We often think about AI getting better because of more data or faster chips. But what if the next huge leap forward isn't about size at all, but about shape? Today we're diving into a research program that asks a pretty radical question. Are we building our AI in completely the wrong geometric universe?
So let's just start with this one idea, because it's right at the heart of everything we're going to talk about. What if the very foundation of how we build AI, the way it sorts and organizes information, is kinda flawed? What if the internal world of an AI just has the wrong shape for the reality it's supposed to understand? And that question leads us straight to the core problem here, this profound mismatch between the geometry inside our AI models and the way human knowledge is naturally structured. It's really a clash of shapes.
Okay, so almost every single large language model you've ever heard of, we're talking GPT, Llama, the whole lot, operates in what mathematicians call Euclidean space. The easiest way to picture it is just a flat, grid-like world. Think of a giant, endless sheet of graph paper, where all the rules are simple and parallel lines never meet.
And this right here, this is where the problem becomes really clear. See, AI's flat space grows polynomially. If you have a square, its area grows by the radius squared. But our knowledge, it's not flat at all. It's hierarchical. It grows exponentially, kind of like a family tree. You start with animal, right? And that branches into mammal and reptile, which then branch out again and again into dog and snake. The number of ideas just explodes with every single level. So trying to cram an exponential tree onto a flat polynomial grid, well, it's just incredibly inefficient.
To make this a little more real, let's use an analogy that I think we all get. It's the age-old problem of trying to make a flat map of our round Earth.
You've definitely seen this on any world map, right? Greenland looks absolutely enormous, like as big as Africa, which it's not. That's geometric distortion. You just can't perfectly represent a curved surface on a flat one without stretching or squishing things. And this research argues that AI is doing the very same thing to knowledge. It's warping the relationships between ideas just to force them onto its flat Euclidean grid.
So, how does AI try to fix this distortion? Well, it basically uses brute force. It just adds a mind-boggling number of dimensions. We're talking 768 or even more. It's like trying to fix that Greenland on the map problem by just using an absurdly gigantic, super high-resolution piece of paper. It's expensive, it uses a ton of energy, and it's just deeply inefficient.
And this brings us to a really fascinating thought. What if we just used a different shape? A geometry that's naturally built for this kind of tree-like hierarchical data right from the get-go.
Okay, so let's talk about the proposed solution, hyperbolic space. Now don't worry about complex equations. Just picture the ruffled, curly edges of a piece of coral, or maybe the surface of a horse's saddle. That's a space with negative curvature, and what that means is that it expands exponentially the further you get from the center. It just has way more room than flat space does.
And this is the really beautiful part. The volume of hyperbolic space grows exponentially, just like the branching structure of our knowledge. It is, and this is the crucial point, a perfect match. The structure of our knowledge is the lock, and it looks like hyperbolic geometry might just be the key.
So what does this perfect fit actually achieve in practice? Well, the results are pretty incredible. This research program managed a 24 times compression. They took a standard 768-dimension representation and distilled it all the way down to just 32 hyperbolic dimensions. And the craziest part? They did this while keeping over 97% of the original model's ability to understand meaning. This isn't just some tiny tweak, it's a potential leap in how efficient these systems can be.
But look, one impressive experiment doesn't change an entire field. For an idea like this to be truly useful, it needs a rock-solid foundation. And that's why these researchers are proposing more than just a new technique. They're actually laying out the pillars for a whole new field they're calling geometric intelligence.
So this proposed field is built on three main pillars. First up is compression, creating a reliable way to distill knowledge from existing flat models into this new curved space. Second is governance, developing ways to control the geometry to make sure it's stable and doesn't spit out weird errors. And third, and this is absolutely crucial for any real science, is falsification, building tough, rigorous tests to prove the results are actually legit, not just some statistical fluke that happens to look good on a chart.
Now, what's really cool about this whole approach is that you don't have to train a massive AI from scratch.
a process that can cost millions of dollars. Instead, this method proposes distilling the knowledge from powerful models that have already been trained. This makes the whole idea way more accessible and a lot cheaper to experiment with.
So to kind of sum it all up, this isn't the first time people have looked into hyperbolic embeddings, but this research program, it feels like a major step forward. Instead of training from scratch, it distills. Instead of only looking at how well it performs a task, it adds these tough geometric validation tests. And it's not just about embeddings anymore, it's about specifying a potential architecture for a full language model that is hyperbolic from the ground up.
Of course, anytime you have a proposal this big, it's going to come with risks and a lot of unknowns. You know, a key part of good science is being honest about what you don't know. And this research program is very upfront about the potential challenges.
The researchers are really clear on this. This is a hypothesis, and it could turn out to be wrong. Hyperbolic geometry seems great for hierarchies, but what about other kinds of data? Will it work for everything? We don't know. Also, the math involved is just more complex and runs slower on today's hardware. It's totally possible that the extra computational work could cancel out the benefits you get from using fewer dimensions. These are big, open questions that still need to be tested.
And all of this leaves us with one last, really provocative thought. We've been talking about efficiency and compression, right? But what if changing the fundamental geometry of an AI does more than just change its performance? What if it actually changes how it represents the world? I mean, if an AI learns in a fundamentally different shape, could it begin to reason, to connect ideas, and maybe even to think in ways that are entirely new to us?
These are some pretty deep questions, and this line of research is really just at the very beginning. So this has been our look into the emerging idea of geometric intelligence. If you want to go way deeper and check out the math and the code for yourself, the entire research program is open source. The link is right there on your screen. Thanks for joining us.